Hi everyone, my name is Katarzyna and I'll be presenting my final project for comparative effectiveness taught by Professor Abdul Hafeez. The title of my project is Using the DEMI Algorithm for Home Diagnosis of COVID-19. Specifically, how can we use casual AI combined with a large language model to predict the probability that someone has COVID-19 just from the symptoms they can observe at home? Let me walk you through what the problem is that we're trying to solve, how we built the system, and then the results that we got. So let's start off with the problem. COVID-19 is very difficult to diagnose at home. A lot of the symptoms, such as fever, cough, fatigue, loss of smell, overlap with things such as influenza, RSV, or even seasonal allergies. And then traditional symptom checkers aren't reliable because they treat each symptom independently without understanding how the symptoms relate to each other casually over time. On the left hand of this slide, you will see the core challenge. Patients who aren't sure whether they have COVID often make one of two mistakes. They either rush to the emergency department unnecessarily, or they wait too long and miss the window for early treatment. Both of these outcomes are expensive for hospitals and harmful for the patient. On the right side, you could see our solution. We built an AI tool that uses the demi-casual algorithm combined with a large language model, specifically Cloud from Anthropic, to take patient-reported symptoms and return a COVID-19 probability score, along with plain English explanation of what score means and what the patient should do next. To provide you with a sense of scale for this problem, there are some statistics we can look at. So 30% of COVID-19 patients present atypically, so their symptoms don't fit the so-called classic profile. They may have neurological symptoms, GI symptoms, or just fatigue without, the expected cough or fever. So it makes triage very difficult. Secondly, at-home rapid tests have false negative rate of up to 21%. So even if someone tests negative at home, there's a chance they may actually have COVID, and we can't rely on that test alone. Thirdly, AI-assisted triage tools have been projected to reduce unnecessary emergency department visits by 15 to 20%. And that is kind of the impact we're targeting with this project. The core of our project is the DEMI algorithm, and it stands for Directed Expectation Maximization for Inference. It's a casual AI algorithm developed by George Mason University that models variables in temporal order, meaning it respects the sequence in which information becomes available. So we organized all 472 variables from the COVID care dataset into 5 tiers. Tier 0 contains demographics, things that are fixed at birth, like age, sex, and race. These came from 27 variables. Tier 1 contains vaccination history, 50 variables about COVID and flu vaccine status. Tier 2 is the largest tier, 377 symptom and exposure variables that patients self-report. Tier 3 contains at-home test results, 17 variables capturing rapid test outcomes, and Tier 4 is the single outcome variable, PCR test positive. The key insight of DEMI is that a low tier variable can actually influence a higher tier variable, but not the other way around. So, for example, your vaccine status, which is Tier 1, can influence your symptoms, Tier 2, but your symptoms can't retroactively change whether you were vaccinated. So, we applied 4 temporal rules to all 70,983 pairwise variable combinations in the knowledge base to enforce this casual direction. This is what makes DEMI fundamentally different from a standard machine learner classifier. So after the DEMI model produces a probability score, we needed a way to make that number meaningful to a patient who isn't a data scientist or a clinician. That's where the large language model comes in. We integrated the Cloud API from Anthropic directly into our notebook. After the model outputs a probability, let's say 38%, the large language model receives that score along with context about the patient's vaccination status, at-home test result, and a symptom description. The large language model returns 3 things: an explanation of what the probability means, a specific recommendation for what the patient should do next, and then a disclaimer reminding them that A is not a substitute for professional medical advice. And then on this slide, you could see a real example with no symptoms reported. The model returned a 38.08 probability, which the large language model classified as low to moderate and recommended monitoring for 5 to 7 days. This is a clinically appropriate response for a baseline scenario. So the entire project is deployed on GitHub and runs in a GitHub code spaces, meaning anyone can open it in a browser without installing anything locally. My repository contains 5 files. The main notebook, COVID analysis, contains the complete DEMI pipeline plus the large language model integration. Merged CSV file is the COVID care knowledge base with 70,983 variable pairs. The COVID care submission CSV contains the raw patient data, 822 patients and 472 variables. We have the survey dictionary CSV provides a variable and definitions, and the requirement text lists all Python dependencies. And lastly, I included a README, which is a description of how to run everything. I'm going to do a live demonstration, and I'm just going to walk you through everything that we're going to go through. Step 1, which is all 4 data files are verified and loaded. You'll see the confirmation that the raw data has 822 patients and the knowledge base has 70,983 pairs. Step 2, we run the DEMI algorithm. Step 3, the 3 models are trained. Step 4, a causal network diagram is generated. And step 5, the large language model interpretation. So I'm going to go through my GitHub repository. And this is right over here. I named it analysis. We're going to go ahead and click that. And this shows our 6 files that were loaded. I did so by hitting add file and upload files. And this is the README that I included. It describes what the project does, the files, how to run it, the API key setup, some of the results and additional information regarding the project. So we are going to enter code spaces now so we can run everything. Hit code spaces. You're going to press this plus sign here. This sometimes takes a little while to load, and if there are any parts that are taking a while to load, I'm going to go ahead and skip through the loading process so we could get to the important parts. So we're going to go ahead and right click. So this README portion automatically pops up about the project. We're going to go ahead, right click, select open with, and the option comes up as Jupyter Notebook. You're going to click that. In the terminal down here, you see that it's finishing up loading, and then we're going to select our kernel here on the right hand side. Okay, so we're going to go ahead and select our kernel. Going to click Python environments, select this here. Okay, I think we're good to run all. And now this is going to take maybe 2 to 4 minutes to load everything entirely. So I'm going to go ahead and skip to the part where we have all of our outputs. Model results that we will go over in the next slide in more detail. These are the top predictors. We have our network model that was created. And then lastly, this is what our large language model integration is going to look like. And this is the interpretation of the results. So we gave it instructions on what we want. And then this is kind of the output that it gives us. It gives us the COVID-19 result interpretation, what the probability means, what you should do next, and the limitations. So yeah, next we're going to jump into some more slides. XGBoost performs best overall, and then we have logistic regression, and then lastly is lasso. XGBoost performed with 0.948 AUC and explaining for 56.5% of outcome variance as measured by the McFadden R-squared. Looking at the top predictors on the right-hand side of the slide, the strongest positive predictor was neurological symptom variable with a coefficient of 1.066. This is clinically consistent with what we know about COVID-19, which frequently causes neurological symptoms like brain fog and confusion. The second strongest was at-home positive confirmation. And then we have negative coefficients like the blind variable, which indicate variables associated with COVID negative outcomes. To wrap up, here are the key takeaways from this project. First, the demi-causal algorithm successfully modeled COVID-19 probability using real patient data, achieving an AUC of 0.948 with XGBoost. The causal tiered structure enforces temporal precedence, which makes the model more interpretable and clinically meaningful than a standard black box classifier. Second, neurological symptoms and at-home test confirmation were the strongest direct predictors of PCR positivity, consistent with established clinical literature on COVID-19. Third, the Claude LLM integration successfully bridges the gap between a raw probability number and a patient-friendly recommendation, making this tool potentially usable by non-clinical users in a home setting. The full code base is publicly available on GitHub and runs in the code spaces without any local setup. Thank you.